If a quantity y depends on and varies with a quantity x, then the rate of change of y with respect to x is dy over dx. Example, rate of change of pressure P with respect to height h is dp over dh. Now, a rate of change with respect to time is usually called as the rate of change, the with respect to time being assumed. We have here two examples. First example, rate of change of current I is di over dt. Another example, rate of change of temperature theta is d theta over dt. In our study, there are some important formulas that we need to remember. Number one, the area of a circle. That is A equals pi r squared. R here is the radius. Second, the volume of a cube. This is the formula. V equals S cube. S here is the side of the cube. Number 3, the volume of a sphere. V equals 4 over 3 pi times r cube. R is the radius. Let us see how to solve related rates problem. Step 1. Assign symbols to all variables involved in the problem. Draw a figure if applicable. Step 2. State, in terms of the variables, the information that is given and the rate to be determined. Step 3. Find an equation or formula relating the variables introduced in step 1. Step 4. Using the chain rule, differentiate both sides of the equation found in step 3 with respect to the independent variable. In here, the independent variable is the time. Step 5. Substitute all known values into the equation from step 4. Then solve for the unknown rate of change. Example 1. A spherical balloon is being filled with air at the constant rate of 2 cubic centimeter per second. How fast is the radius increasing when the radius is 3 centimeter? For our solution, the step 1 says, assign symbols to all variables involved in the problem. Draw a figure if applicable. We have a figure here, and it shows that as the balloon is being filled with air, both the radius and the volume are increasing with respect to time. We let V be the volume and R equals the radius. Step 2. State, in terms of the variables, the information that is given and the rate to be determined. Analyzing our problem here, this 2 cubic centimeter per second is the rate of change of the volume with respect to time. So that is dV over dt equals 2 cubic centimeter per second. And in our example here, we are required to get the rate of change of the radius with respect to time. So that is dr over dt equals question mark. Step 3. Find an equation relating the variables introduced in step 1. We know the formula of the volume is equal to 4 over 3 times pi r cubed. Step 4. Using the chain rule, differentiate both sides of the equation with respect to independent variable. The independent variable here is the time, denoted by t. So let us now take the derivative of this equation with respect to time. So we have dv over dt on the left side is equal to the constant 4 over 3 we copy down here, and then we will take the derivative of r cubed with respect to the chain rule. So the 3 cubed now becomes 3 r squared and then multiplied by dr over dt. Of course, that pi is part of our answer here. Simplifying further, we can cancel this 3 and the denominator 3. Simplifying our formula now, we have dv over dt equals 4 pi r squared times dr over dt. Step 5. Substitute all known values into the equation from step 4. Then solve for the unknown rate of change. In our problem here, the radius is given as 3 cm. Substituting now the corresponding values in here, the dv over dt is now 2 cubic centimeter per second equals the 4 pi we copy here, and the r squared we substitute the 3 centimeter square times the dr over dt. Simplifying the square here, we can show that we have 3 square times centimeter square. Let us simplify the units of measurement by cancelling this centimeter square, and the exponent 3 here becomes 1. So the new formula now is 2 centimeter per second is equal to 36 pi times dr over dt. We want this value dr over dt. Let us divide the equation by 36 pi. So we have now 2 over 36 pi centimeter per second is equal to dr over dt. We can still simplify this fraction by reducing to lowest term. So dr over dt is equal to 1 over 18 pi centimeter per second. This is the rate of change of the radius when it is equal to 3 centimeter. This is our final answer. Example 2. An airplane is flying overhead at a constant elevation of 4,000 feet. A man is viewing the plane from a position 3,000 feet from the base of a radio tower. The airplane is flying horizontally away from the man. If the plane is flying at the rate of 600 feet per second, at what rate is the distance between the man and the plane increasing when the plane passes over the radio tower? For our solution, step 1 says, assign symbols to all variables involved in the problem. Draw a figure if applicable. This is our figure. An airplane is flying at a constant height of 4,000 feet. the distance between the person and the airplane, and the person and the place on the ground directly below the airplane are changing. We denote those quantities with the variables s and x respectively. Step 2. State, in terms of the variables, the information that is given and the rate to be determined. Since x denotes the horizontal distance between the man and the point on the ground below the plane, we say that dx over dt is equal to the speed of the plane. And on the problem, it is given as 600 feet per second. Since we are asked to find the rate of change in the distance between the man and the plane when the plane is directly above the radio tower, we want to get the ds over dt. That is when x equals 3,000 feet. Step 3. Find an equation relating the variables introduced in step 1. Looking at our figure here, we can deduce a right triangle. And by Pythagorean theorem, we can write x squared plus 4,000 squared is equal to s squared. Step 4. Using the chain rule, differentiate both sides of the equation with respect to independent variable. We say that the independent variable here is the time, denoted by t. So taking the derivative now with respect to time, the derivative of x squared with respect to time is 2x times dx over dt plus the derivative of 4,000 squared is 0 because this is a constant. So no need to write the plus 0 on the left, equals the derivative of s squared with respect to time is 2s times ds over dt. We can simplify further this equation by dividing by 2. So we have now x times dx over dt equals s times ds over dt. Step 5. Substitute all known values into the equation from step 4. Then solve for the unknown rate of change. Observe our equation here. The value of x is 3,000. dx over dt is this 600 feet per second equals the value of s is unknown. And this ds over dt is what is required in the problem. We need the value of s. With regard to the figure here, when x is equal to 3,000, we can get the value of s with respect to the Pythagorean theorem. Substituting the values, we may write 3,000 squared plus 4,000 squared is equal to s squared. Simplifying and getting the value of s is equal to 5,000. Let us note this value of s in here. Now, we are ready to do the substitution. So the x now becomes 3,000 feet the dx over dt is the 600 feet per second equals the value s is now 5,000 feet times ds over dt. Simplify further by cancelling the unit of feet to each side of the equation. And then let us get the product of the 3,000 by 600. So we have now the product as 1,800,000. We want the value of ds over dt. Let us divide the equation by 5,000. It means this 5,000 will be the divisor of this value 1,800,000. So ds over dt is equal to 360 feet per second. This is the rate of the increasing distance between the man and the plane. This is our final answer. Example 3. Find the rate of change of the area of a circle with respect to its radius r, when r equals 3 centimeters. The problem talks about the area of a circle. Therefore, we need the area formula. So it is here. Then let us write the given. The only given here is the radius, that is 3 centimeter. In the problem, we need to find the rate of change of the area. So that is the dA over dr, and that is what we want to know. Next step, we differentiate the formula with respect to r. So the left side is dA over dr equals the right side. Derivative of pi r squared is 2 pi r. And from here, we substitute the value of r as 3. R is here, so it becomes 2 pi times 3. 2 times 3 will be 6, and we attach the pi. This is our answer. The unit of measurement is centimeter. This is how we interpret it. The area is increased by 6 pi centimeters for every 1 centimeter increased in radius. Example 4. The side of a cube is increasing at a rate of 4 centimeters per second. Find the rate of change of the volume of the cube when each side is 5 centimeters. The problem is talking about the volume of a cube. Therefore, we need a formula for that volume. So this is the formula. Then let us write the given. Look at the first sentence. The side of a cube is increasing at a rate given. This is about the ds over dt. And the value is 4 centimeters per second. Note that there is a word increasing here. So we write a positive value for number 4. But in some problem, you might find the word decreasing. If that happens, the 4 here will be negative. So we keep the positive because of this word increasing here. Another given is the side, that is 5 centimeters. In the problem, we need the rate of change of the volume. That means we need the dV over dt. Next step, let us now differentiate both sides of the equation with respect to time t. So this is our formula. The left side becomes dV over dt equals the right side, we apply the chain rule. So the s cubed becomes 3s squared times ds over dt. And from here, we're going to substitute the given values. Therefore, the s is now changed into 5 and the ds over dt is now 4. Simplifying further, 5 squared is 25, then the final product is 300. Our unit of measurement, cubic centimeter per second. Example 5. The radius of a circle increases at a rate of 2 meters per second. Find the rate at which the area of the circle increases when the radius is 5 meters. The problem is talking about the area of the circle, so we need that formula, and we write it here. Then let us list the given. First, in the first statement, the radius of a circle increases at a given rate. So that means it is the dr over dt equals the 2 meters per second. Another given is the radius, that is 5 meters. In our problem, we need the rate at which the area of the circle increases. That means let us find the dA over dt. Next step, let us differentiate both sides of the equation with respect to time t. So this is our formula. The left side becomes dA over dt equals, the right side now becomes 2 pi r times dr over dt. Let us now substitute the given values. The r becomes 5 and this dr over dt is now 2. Simplifying, we get the final product as 20 pi. The unit of measurement is square meters per second. Example 6. The radius of a sphere decreases at a rate of 2 meters per second. Find the rate at which the volume decreases when the radius is 5 meters. The problem is talking about the volume of a sphere. So we need the formula for that volume, and it is here. Then let us write the given. Look at the first statement. The radius of a sphere decreases at a given rate. So that is the dr over dt. Now, take note, we have the word here, decreases. In that case, it denotes a negative value. The given value here is 2 meters per second. So because of the word decreases, we write the negative 2 meters per second. Next, another given is the radius, which is 5 meters. And in the problem, we are required to find the rate at which the volume decreases. That means we need the dV over dt. Now, next step, let us differentiate both sides of the equation with respect to time t. So this is our equation. The left side becomes dV over dt equals, the right side, this 4 over 3 pi is a constant, so we copy it here, times derivative of r cubed, so we have this 3r squared, times dr over dt. We can simplify the right side. We can cancel this number 3 and the 3 in the denominator. From here, we can substitute the given values. First, we copy the 4 and pi, it's here. Then the r squared becomes 5 squared. And this dr over dt, we now write the value negative 2. 5 squared is 25, and the final product is negative 200 pi. Unit of measurement is cubic meters per second. Example 7. if the radius of the circle is increasing at the rate of 0.7 centimeter per second, at what rate its circumference be increasing? Our step 1 is to identify the formula. The problem is mentioning about circle and circumference. In this case, we're going to use the formula for circumference of the circle, and that is C equals 2 pi r. Next step, we're going to write the given. There is one number that is 0.7 as given. If we analyze this, it says the radius of the circle is increasing. That means this is the rate of change of the radius with respect to time. So we write dr over dt equals 0.7 centimeters per second. And the problem says about rate of change of circumference. That means that is d of c over dt. This is what we want. We're going to differentiate now both sides of the formula or equation with respect to time t. So this c becomes dc over dt equals, these 2 pi are constants, so we put them in the front, times derivative of r, that would be 1, times the dr over dt. Then we substitute the given value. There is a 0.7 for this dr over dt. So we have 2 pi times 0.7. And the product is 1.4 pi. Unit of measurement is centimeter per second. This is the answer. Example 8. A pebble is dropped into a calm pool of water, causing ripples in the form of concentric circle. The radius r of the out ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? For our step 1, let us identify the formula to be used. The formula mentioned about circle and about the area. So that means we're going to use the area of the circle. We have A equals pi r square. Step 2, we're going to identify the given. There is one value here, 1 foot per second. This is the radius r of the out ripple is increasing. That means this value describes the rate of change of the radius with respect to time. So we write dr over dt equals 1 foot per second. Another given is the value of the radius. So r equals 4 feet. The requirement of the problem is the rate of change for the total area. So that means we need the dA over dt. Next is we differentiate both sides of the formula or equation with respect to time t. So this a on the left, it becomes dA over dt equals the pi r squared. Pi is a constant, the power 2 comes down, and the r. Then 2 minus 1 is 1 times the dr over dt. Then we substitute the given values coming here. So we have 2 pi, the r now becomes 4, and dr over dt is 1. When we simplify this, we get 8 pi. Unit of measurement is feet square per second.